This is the second of two videos working through a complete setup and solution process for a frame problem consisting of two frame elements. In the prior video I set up the problem, and in this one we will work through the solution. Just as a reminder, this is the problem that we're solving. It consists of two elements and three nodes. Lengths are shown, we have boundary conditions known, and we already developed stiffness matrices and the global force vector to solve the problem. We came up with a global stiffness matrix with the boundary conditions removed. In other words, we're ignoring the rest of the stiffness matrix for right now, the portion of the matrix that deals with nodes 1 and 3, because that doesn't matter for us to find the unknown degrees of freedom. We will, of course, need to refer back to those terms that I haven't captured here when we're finding reactions. Plugging in the numbers for this problem, we get a numerical stiffness matrix. And this points out something interesting with beam elements. The units are different for the different terms in the stiffness matrix for a beam element. And this is because the beam element has axial or translation degrees of freedom, axial and transverse, but it also has rotational degrees of freedom, which have different units for their stiffness. And that's why we end up with this mix of units in a beam element stiffness matrix. In addition to the stiffness matrix, we also need the force vector. Let's focus just on the elemental load vector. So these are the nodal loads that were developed from the distributed load. The reason I'm focusing on this is that I just need the force terms that are associated with node 2. Plugging in the numbers here for the distributed load and the lengths, I can calculate the total distributed force vector, but just then isolate the last three terms, which are the ones associated with node 2. Those are the ones I need to put together with the reduced stiffness matrix in order to solve the problem. So then I can state my problem, the reduced problem, just focusing on unknown degrees of freedom, as KBC times DBC equals FBC, where BC refers to boundary condition conversion. So with the numerical values in, this is the system of equations I now need to solve. I'm not going to go through the solution process for this. It is a straightforward 3x3 matrix solution. It's three equations, three unknowns. If you use Gaussian elimination and back substitution, you quickly find the unknown degrees of freedom are d2x is equal to 0.598 inches, d2y negative 1.82 inches, and phi, the slope at node 2, slope change rather, is 0.0294 radians. So I get a large amount of deflection downward and a smaller amount positive to the right. Let's now move on into the post-processing. So this completes the main part of FEA, the solution for the unknown degrees of freedom, but of course we want to know more. So we're going to look at stresses and then reaction forces in this problem. So first off, we'll consider the stresses. We have a general formula that came from the total potential energy formulation. So the stress vector is equal to the D matrix times the B matrix times the T transformation matrix multiplied by the portion of the global degrees of freedom that are applicable to this element. Now this all simplifies, of course, for a beam element. Specifically, it is no longer a stress vector. We have just one stress term for the element, sigma x. But unlike the bar element, because the beam element has cubic shape functions, we actually have stress that depends on position in the beam, not only axial position, but also the distance from the neutral axis, the y variable inside the beam. So this is our full expression when, this identifies that D is equal to the Young's modulus E, and then I've plugged in what B is for a frame element. T we haven't talked about yet. So now taking the derivatives that are indicated there for each of the shape functions, I get the full expression in terms of x, y, and L for the stress. So the last thing I need to do is do the conversion in the T. So this expression here is going to give us the stress at any point inside the frame element. Let's try a particular point. For example, let's look at the stress just to the right of the joint, or in other words, right at the left end of element 2. In order to evaluate that, the transformation matrix goes away. It becomes the identity matrix. And we're going to set x in element 2 equal to 0. So when we do that, we get a reduced form of the B matrix because we're evaluating it at a specific X location. And then I need to consider what D is equal to. I've added that up at the top. This is the D values that are relevant to this element. It's not all of them. Remember, the B is a row matrix here, and it consists of 6 terms. I'm only showing you 3. Of course, I'm doing that because we know that the other 3 are equal to 0. Then we also have the length of 180 inches. We can plug all those in, and we get this expression for the stress. So I've evaluated the E and the L and left the Y's at the moment in there, and I've added in the vector of the degrees of freedom, where the first 3 terms are the displacements at node 2 and the last 3 zeros are the displacements at node 3, because we know that's fixed. Multiply these two out and I get an expression for the stress at this location, and of course it depends on our position relative to the neutral axis. So we'd plug in for y usually the half of the height of the section in order to find the peak stress. You can see here as well that it is negative, so it's compressive for the 100 term. The 100 term, by the way, is the axial piece, and the 9.5y is the bending piece. So to finish up the post-processing, let's go and look at reaction loads. I just want to remind you that the full force vector consists of a summation of all of the elemental distributed load force vectors together with the nodal forces or point forces that we have from the initial model. So now that we know D, we can move all of those elemental force terms over to the same side as KD, and we can solve just for the point loads because the reactions are the point loads. We need to subtract out the terms that come from the distributed loading. Those showed up at the same location as the reaction forces, but they are not part of the reaction. So again, this summation over I of Fi, those are the nodal forces that came from the distributed loads. So I'm looking for just the reaction loads, and that's going to be equal to some big K matrix that I have not yet written out because it just ended up being too messy and I didn't want to do that. And it's going to be multiplied by the degree of freedom vector, where 6 of the 9 terms are 0, but the middle 3 we now know, we've solved for those. And we're then going to subtract out the nodal forces that came from the distributed loads, and I've listed those here. These are the ones for element 1, because that's the only element that had the distributed load applied. So that's the setup. Element 1 is going to contribute to the upper left corner. Element 2 is going to contribute Ks to the lower right corner of the stiffness matrix. But if I look now, specifically, let's see node 1. I just want to look at node 1. That means I really just need to focus on the top 3 equations. And you notice that element 2 doesn't contribute to those. So I can focus, to get the reactions at node 1, I can just focus on the stiffness values that come from element 1. Notice that, in fact, because I've got a whole bunch of zeros there, I'm just looking at the terms identified. And the other thing that we can notice is that the first 6 terms of the degree of freedom vector are the only ones I need to focus on, and 3 of those are 0. So it's going to get a little bit simpler. But basically, again, what I'm looking at are the first 3 rows of this. Okay, so I'm going to lay out that solution process. I extract just those first 3 rows, and that gives me the simplified equation here, where the 2 force vectors, the one on the left that I'm looking for and the one on the right that came from the element 1 distributed load, those are just 3 terms in the column vector. But then I have 6 columns in my stiffness matrix and 6 rows in my degree of freedom vector. The first 3 rows are going to eliminate the first 3 columns of the stiffness matrix, but I'll keep them for right now. Plugging in what those terms are. Remember, this is just the terms that came from element 1 stiffness matrix. So these are the first 3 rows of the element 1 stiffness matrix. I can then plug in the values for E, A, I, and L1, and also plug in for the degrees of freedom that I've now known, and the node 1 forces from the distributed load. So remember, we had a total of 6 forces that we found from the distributed load. I now need the first 3 of those that are associated with node 1. And I want to put that all together, and I can solve for the reactions. So putting it together, this is what my equation looks like with all the numbers plugged in. I perform the multiplication and the subtraction at the end, and I find my reaction forces as shown here. We can do a quick check of the directions. If I apply this vertical force downward, that would certainly tend to move node 1 to the left, so I have to put a positive R1x to keep it there. Obviously, I have to push upward from the ground, so I have a positive force upward, and then the bending moment as well as a positive bending moment. So this gives me the process, or shows you the full process of setting up, solving, and post-processing a frame element. As you can see, even though this is still a 1D element, this is starting to get pretty complicated, and this is why we are very thankful that we have computers to do FEA. We aren't doing all this by hand. This is about as far of complexity of hand calcs as I will do in this lecture series. Later on, we'll be talking about specific concepts, but we won't set up and solve full solution problems because it simply is too cumbersome for large numbers of degrees of freedom.